So what if our entire universe wasn't a vast empty void at all, but was actually a single giant drop of some bizarre quantum liquid? It's a wild idea, I know, but today we're diving into a theory that treats the vacuum of space exactly like that, like a superfluid. And this one strange idea might just solve two of the absolute biggest puzzles in modern physics. Okay, let's get into it.
First things first, we've got to ask a question that seems almost simple. Is space really empty? You know, for centuries, we've pictured it as this perfect, black, empty stage where all the stars and galaxies play their part. But what if that stage, what if the emptiness itself, is actually the main character in the whole story?
Well, quantum field theory comes along and completely shatters that old picture. It tells us that the vacuum, what we think of as nothing, is anything but. It's actually a seething, boiling sea of energy with these tiny virtual particles constantly popping into and out of existence. This energy that's just inherent to empty space, we call it vacuum energy.
And this is where we smash headfirst into a giant wall. Because when physicists do the math and calculate how much vacuum energy should be out there, they get an absolutely colossal number. I mean, a number on the most fundamental energy scale possible. But when astronomers actually go and measure it by looking at how the universe is expanding, the number they find is just incomprehensibly smaller.
How much smaller, you ask? 120 orders of magnitude smaller. That's a 1 with 120 zeros after it. This insane gap between theory and reality is called the cosmological constant problem. And it's not an exaggeration to say it's been called the single worst prediction in the entire history of physics. It's a mystery that has kept physicists up at night for decades.
So, where do you even start with a problem that big? Well, the clue might be hiding in one of the coldest and, frankly, weirdest places on Earth, in the world of superfluids.
So what in the world is a superfluid? It's a state of matter, a liquid, that has absolutely zero viscosity, zero friction, zero internal resistance. It's a special substance where the bizarre rules of the quantum world suddenly become visible to the naked eye, on a scale you can actually see.
And trust me, this stuff is just strange. If you take superfluid helium-3, for example, it can flow on a circle forever without ever slowing down. It can literally crawl up the walls of a beaker and spill out the top, totally defying gravity. The whole blob of liquid acts like one single unified quantum object. It's almost like magic. And that brings us to the big what if at the heart of this whole theory. What if the quantum vacuum, the very fabric of space-time itself, has these same properties? What if our entire universe is, at its most fundamental level, a superfluid?
Okay, let's take that idea and run with it. Let's see how picturing the universe as a liquid drop can tackle that insane 120 orders of magnitude problem we started with, the cosmological constant problem.
So the theory models the vacuum as a self-sustained medium. A great way to think about this is to picture a drop of water just floating around in the International Space Station, right? It holds itself together. It doesn't need a cup or a container. The idea here is that our universe is just like that drop. It exists all on its own, perfectly in balance, with nothing outside of it pushing in. Now here's where some basic high school thermodynamics gives us a huge clue. For that floating drop of water to be stable, to not be expanding or collapsing, its internal pressure has to perfectly balance the external pressure. Well, since there's nothing outside our universe drop, the external pressure is zero, which means for it to be stable, its internal pressure must also be zero. And here's the kicker. In cosmology, the vacuum's internal pressure is the cosmological constant. So get this, that enormous, gigantic vacuum energy that quantum theory predicts, it's still there. But in a self-sustained system like this, it's just automatically and perfectly canceled out by the vacuum's own internal structure. The system just naturally finds its way to a state of zero total pressure. You don't have to fine-tune anything, it just works. And this also explains why the value we measure today is so incredibly close to zero. I mean, our universe is unbelievably old. It's had billions and billions of years since the Big Bang to just relax, to settle down into its most stable, lowest energy state. And for self-sustained liquid, that state is, you guessed it, zero pressure. Okay, so that is a beautifully elegant solution to the cosmological constant problem. But that's only half the story. What about physics' other great headache, the hierarchy problem?
The hierarchy problem is all about mass. You see, our best theories suggest that when fundamental particles, like electrons, interact with that super energetic quantum vacuum, they should soak up a ton of energy and become incredibly heavy, like 10 quadrillion times heavier than they actually are. So the huge question is, why are they so ridiculously light?
Well, according to this theory, the answer lies in something called topology. And don't worry, it's not as scary as it sounds. Just think of it like this. A coffee mug and a donut are topologically the same because they both have one hole. You can squish and stretch one into the other. But you can't turn a sphere into a donut without ripping it. Topology is about those fundamental properties that you can't change. And the idea is that our superfluid vacuum has its own unchangeable fundamental structure. And that structure is what keeps particles light. The specific topology of our vacuum creates these special little nodes called Fermi points, which you can see on the left. Think of them as tiny protected zones in the liquid of spacetime where particles are literally forced to be massless. It's a rule that's baked into the very fabric of the vacuum. If that topological feature wasn't there, you'd get what you see on the right, a Fermi surface, and particles would instantly gain that enormous mass the theories predict. So in other words, the fact that particles are so light isn't some weird cosmic accident that we have to explain away. Nope, it's a direct, unavoidable consequence of the fundamental geometry, the fundamental shape of the vacuum itself.
So we have this one, single, powerful idea, the superfluid vacuum, and it seems to elegantly solve two of the biggest headaches in all of physics. But the implications of this, well, they go even deeper, and they are truly mind-bending.
Let's just do a quick recap of the logic. It's beautiful. We start with one core assumption. The vacuum of space is a self-sustained liquid-like medium. Boom! From that, simple thermodynamics naturally explains why the cosmological constant is zero. And then, its fundamental topological structure naturally explains why particles are so incredibly light.
And this leads to the most profound consequence of all. If this theory is right, then everything we've always thought of as fundamental, electrons, photons, quarks, all the forces, they aren't fundamental at all. They're what we call emergent phenomena. They're like the waves and the ripples on the surface of a much, much deeper underlying reality, the vacuum ocean itself.
The physicist who pioneered this work, Volovik, puts it perfectly. He says that even gravity, as described by Einstein's general relativity, isn't some fundamental force of nature. It's just an effective theory, a side product that emerges from the collective behavior of that deep vacuum liquid.
Which, of course, leaves us with one final staggering question to ponder. If our entire reality, all the matter, all the forces, maybe even space-time itself, is just an emergent property of this deeper quantum vacuum, then what's underneath it all? What, if anything, is truly fundamental?